Good morning, all the participants and listeners. So I'm Sanjay and welcome you all in this second part of the tutorial, that is one class classification models, that's specifically known as the target class learning. We'll discuss and we'll see that how this phenomena will work out to identify the anomaly in different application domains. So let us start. So if we are saying that we are looking for target class, so the target class itself says that the class of interest where we have more interest towards that class. So that's known as the class of interest. And the samples are known as the class of interest samples or COI samples. So assume that we have a single class sample the samples of a single class. That means that class is known as the target class, and the other class sample is assume that they are not at all present, or if they are present, they are poorly sampled or ill-defined. Then the other class samples, which is not at all exist or poorly sampled, so they are known as the anomaly. So in that case, we should think of that how we should learn this target class so that at later stage of testing, we can easily identify that yes, the incoming sample is anomalous one, okay, and doesn't belong to the target class. That is why uh, this target class learning is very important in anomaly detection techniques, because it is in most of the cases, most of the practical application, even in our natural wisdom also, we always think sort of target class learn. And in that way, once we learn the target class very efficiently, then only we'll able to identify that yes, the sample which is not at all belong to the target class is definitely is an anomalous one. Okay. So if you talk about the target class learning, so apart from the classification or clustering or self-supervised learning, anything, but if you talk about the learning, that means we should learn or we should learn the target class more efficiently. And to learn the target class, definitely two things are very important. The first one is the samples, and the second one is features. If you see this diagram, the colored samples are basically, we can assume that these are the you can say the target class samples, and the black dot is here is representing you the anomaly. So the basic idea that how we should learn the boundary that will be covering this target class very efficiently, such that any incoming sample, if it is anomalous, it should be falling outside of this boundary. Okay. So in this case, the objective of target class learning is to learn the characteristics and behavior of the target class very efficiently. Okay. So if we look for to learn the target class very efficiently, then definitely there are two things that we should identify the most promising class of interest samples that will be describing the target class itself, along with the most discriminant features that are responsible to represent the target class. So in upcoming slides, we'll see that how these things can be done. Okay. The second thing is that why don't we go for the conventional machine learning algorithms? Because the conventional machine learning algorithm says that at least you must have at least two well-defined set of classes or samples, or two classes at least, such that your model get trained, and at that time you can test the sample whether it belongs to class A or class B. But what will happen in that case? Suppose a sample that is coming belongs to class C. As you have trained your model or conventional machine learning algorithms, like suppose binary or multi-class classifier we use, if you talk about the supervised learning mode, then let us assume that we are using the binary classifier and we are training our model on class A and class B. Those are well defined. But at the time of testing, suppose a sample that is totally anomalous and it belongs to class C and it arrives for testing. then definitely that conventional machine learning algorithm like support vector machine and random forest or decision tree, those basically these machine learning models simply says that here's incoming sample C belongs to either A or B. So that is surely misclassification and misguided approach. So we should think of that because this sample C that is arriving for testing is surely an anomalous sample, and we should efficiently identify that. In such cases, the conventional machine learning algorithm that fail because what we assume for third class learning that only third class samples are present during the training. That means the class where we are interested that is available for training, and the other class samples may be absent or ill-defined or poorly sampled. So in that phenomena, this third class learning plays a big role towards this anomaly detection. At the same time, if you talk about the presence of deceptive similar classes, then again it leads a big problem because deceptive similar classes says that the class it seems same but they belong to different classes. So in that case also this conventional machine learning algorithm fails. But what is the phenomenon that advanced learning basically provides us that yes, we are focusing on a single class and the rest of the classes will be treated as the anomalies. This phenomena it becomes very tedious and tough to distinguish any anomaly sample when we talk about any distributed environment. So if the samples are arriving from distributed sources, then target class learning becomes more challenging. So we'll see one by one all these things as part of the tutorial. So let us talk about few important challenges in anomaly detection. So surely the anomaly is cannot take fully cannot be processed in fully supervised approaches. Why? Because it is possible that they're not labeled at all. That how we must process. So therefore, that we should go for some unsupervised learning approach, and that will also be focused towards the target class, even though you don't know very much about the number of classes present in the distribution. It is also possible that the anomaly labels are sparse because usually it is done by the human experts. Even it is labeled, like suppose you want to work on supervised domain, the anomaly is rare. And surely, the number of samples belonging to the target class and number of samples belonging to the anomaly class or other class basically are highly imbalanced. And that is why conventional machine algorithm fails to cope up with the situation. Even we can try to some extent via some upsampling mechanism so such that we can balance the available target class and available anomaly class with some extent, but still uh, problem is there to identify the anomaly data. The second thing is that we should learn the high dimensional data patterns of normal data. It is possible that data is coming from some removed uh, images, some removed source images are coming that is of high dimension, or some biomedical images coming of high dimension. Then how we should learn the high dimensional data representations of this normal data, such that later stage we can easily identify that which one is the anomaly and which one is the normal one that belongs to the target class. And the third and most important, that the notion of anomaly cannot be described very well because it is subjective in nature and varies from application to application. And surely the boundary between normal and anomaly is not precise enough, because if it is labeled one, then there is not a big deal. But if it is unlabeled, or suppose we want to work over the unsupervised domain, then surely the anomaly the boundary between the anomaly and the normal data cannot be recognized very precisely. So that is again a big challenge. So let us discuss that how we can cope up with these challenges. Okay, so let us say that if you want to formulate the anomaly detection technique in presence of the target class, that means suppose we have samples of a single class only and we don't have the samples of another class, then how we can model, we can basically formulate any machine learning model. The first, it can be divided into two phases. The first phase is we should learn the target class very efficiently, or we can say we should learn the data pattern very efficiently. Okay? If we assume that we don't have only target class, we have a number of classes in data pattern and data sample, uh, and we are supposed to identify some anomalous data point that will be incoming in future. So phase one, we should map the target class appropriately to the some unified space. It may be the predefined space, it may be the latent space, okay, such that the all the similar points, suppose they belongs to the new target class are coming around, and we can draw somehow the boundary points very efficiently. The second phase is the anomaly detection. Suppose some sample is coming for testing, and we should identify that whether that sample belongs to the in class itself or it belongs to some outlier. It is outlier, it is an outlier. So I'll do that. So definitely some statistical observations must be there in case for a few samples we can compute the anomaly score, we can decide the anomalous behavior based on the distance from the mean of the distribution and so on. So many techniques are available, so we should think on that. Okay, coming back again to the difference between the conventional and the one class classification approaches. Because if you talk about the target class learning, then we are equipped with only single class data. And let us assume that we are working on supervised domain. That means all the samples are labeled. Okay. So if we talk about the conventional classifiers, so we assume that we must have at least two well-defined classes in our data set. If they are not well-defined, or they are balanced, or they are skewed, we should opt some technique uh, to balance the data set first, so that we may have at least two well-defined classes in our data set. Then we may get train our binary classifier, we may get train our multi-class classifier. We have, if you have more than one number of classes. So the best binary classifier, we can say that the Bayesian one or the SVM or decision tree random forest, anything. So the restriction is that the both of the classes must be well defined. But assume the scenario, what will happen? Suppose we don't have, we can say, two well-defined classes. We are equipped with only single class samples. That means only target class samples are available. And based on the learning methodology, we should identify that the incoming testing sample is anomalous or not. So if we are equipped with one class samples, then definitely the classification strategy must fall under one class classification. In diagram, we can see that in this binary classifier, these two classes are defined. In multi-class, there are three classifier classes. You may have a number of classes. Take an example of the most common data set, that is AMNIS. So we have 10 classes. So for that, we can opt for multi-class classification approach. But suppose what will happen? Suppose we'll have one class. So we must try to identify some boundary that will be covering all the data points of the target class. And in later stage of testing, the data point that is not falling inside this boundary may directly concluded as one class, may directly concluded as an anomaly. Okay. So the best examples are, one class support vector machine, support vector data description, isolation forest, Gaussian mixture model, and many more. So we'll see in next upcoming slides. So coming to the taxonomy of this, you can say one class classifiers, where we assume that we are equipped with a single class sample, and based on that, we must learn something so that we're able to identify that the new coming samples are anomaly or not. Okay? So these classifiers may broadly be categorized in three types. The first one is density-based model. The second one is the reconstruction-based model, and the third one is the boundary-based models. Along with in the second layer, we can see that it has been further categorized based on the type of the data, whether it is symbolic one or whether it is the numeric one. Okay. So let us don't follow this type of data right now. If you talk about the density-based algorithm, so as the name implies, the density-based methods are based on the estimation of the probability density function of the feature values in the complete feature space. And suppose if the second class is not at all available, that means in the absence of knowledge about the second class, the PDF or the probability distribution function for the class can be assumed as uniform. Okay, be assumed as uniform, and based on that, it will work upon. A specific form of the distribution of feature value is often unknown, and it is approximated by the mixture of the Gaussian. Okay. So we have a few models here, like we can go for the histogram approach or Markov models or the Gaussian mixture models or Bayesian density estimation. Even though we talk about the k-nearest neighbor, so that is also produced in nature, but anyhow, we are equipped with a single class sample, so this k-nearest neighbor may be working out very efficiently. The second one is the reconstruction-based model. So contrary to the density-based models assumption about the underlying data structures are made. Okay. So we may have several types here. We can go for some association rules. We can go for some time series analysis. We can go for SOM. We can go for principal component analysis. We can go for autoencoders, because ultimate target is to how the incoming sample will be reconstructed. If you're able to reconstruct this sample very efficiently, that means it belongs to the target class. If you won't able to reconstruct the sample efficiently, not efficiently, then we surely say that the incoming sample is the anomalous one. Coming to the third one, that is boundary-based algorithms, and these are the most versatile application algorithms that have been used so far. The examples we can consider the SVDD and one class support vector machine and k-centers. Okay. But most importantly, if you look the literature, we find that the one class support vector classifiers, especially SVDD and one class support vector machine, are most promising in this one class classification approaches. So in this tutorial, we are focusing towards the boundary-based one class classifiers, specifically one class support vector classifiers. Okay, coming to this one class support vector classifiers, if you if you talk about one class support vector classifiers, it is incorporated with the support vector. No? So the ultimate goal is to find out such a boundary that will be covering the target class samples, and the points that will be residing on the boundary of that is covering the whole target class are known as support vectors. So the one class support vector classifiers are basically boundary-based one class classification algorithms, and the boundary points are especially known as the support vectors, as in the case of conventional support vector machine. So there are two benchmark variants of one class support vector classifier. The first one is SVDD, given by Tex and Twee, and the second one was the one class support vector machine, that is some sort of an extension of the conventional support vector machine and known as one class support vector machine. The basic difference between these two algorithms are this, that the SVDD tries to draw one hypersphere as boundary to cover the whole target samples, whereas the one class support vector machine tries to draw one hyperplane such that the target class samples will be separated from the subspace of the origin. So we'll see the explanation of the both of these algorithms one by one. But in this stage, what we can say that these two benchmark variants of one class support vector classifiers are basically one class classification algorithms that will be able to work if only the target class samples are available during the training and the other class samples are not at all available or either poorly sampled. So in such cases, what we can say that the new incoming sample, which is separated from these boundaries that will be drawn by this SVDD and one class support vector machines, are surely be treated as outliers. So coming to the support vector data description, so it was developed in 1999, and till date, people are trying to extend it to it for basically a more robust learning model, if only the data samples are available during the training. So basically, as there is no assumption required initially, but sometimes it is basically it must be assumed that the nature of the distribution was Gaussian of the target class. If it is not, then also we can go for some learning, because we have some mechanisms like SVD, singular value decomposition, and with the help of that, somehow we can try to change the basically the distribution of data to the Gaussian, okay, to some other space, to some other latent space, such that all the similar point of the target class samples will come closer and it will be easy to draw one hypersphere. Okay, so the question is that whether only the hypersphere can be drawn. So the answer is not at all, because we may think of some other, uh, boundary also, like ellipsoidal. Okay, so that is also one sort of extension that can be made to explore the extensibility of this SVDD. So in SVDD, basically one hypersphere is identified with the minimum radius. The objective is to find the one hypersphere with minimum radius to cover all the target class samples. And if any incoming sample, okay, is basically far away or away from the boundary, so we can surely conclude that point as an outlier. So here in this diagram, we can easily see that if the radius of the hypersphere is r, and you can say the distance of xi to a, the center of this hypersphere, is greater than r, then surely the xi will be treated as an anomaly. Suppose we want to formulate this SVDD, then how we can proceed for? So the first objective is the first phase, we should learn the target class very efficiently. And suppose we have, the predefined feature space that is given to us, then we can go for some latent space using some kernel function, okay? The Gaussian or the radial or something else or polynomial, but so it depends based on the nature of the data sets that which kernel function will suit to which data set. But mostly the Gaussian kernel is basically more suited for all type of application. It has been observed. And the second phase is anomaly detection, no doubt. Once we have calculated this hypersphere boundary and the radius and everything. So if any sample X can be declared as anomaly if the distance from the center of the distribution is greater than R. So we can say that X is an anomaly. So this is some sort of mathematical derivation of this SVDD. So the R is from this objective function, we can see this R is the radius. Okay. and this A is the center of this SVDD. So over the past 2 decades, one-class classification became very popular due to its diversified applicability in data mining and pattern recognition applications. And concerning to OCC, one-class support vector classifiers have been extensively studied and improved for the technology-driven application. So especially this base variant of, we can say this one-class support vector classifier that is known as SVDD plays a vital role. So once we'll see that this is R is radius, A is the center. Okay, we should apply some penalty over there, and definitely we should apply Lagrangian and the tool of this objective function will be like this. Okay. So we are not going to detail for this, applications, this derivations, but this is we should concentrate on this, focus on this objective function that the radius will decide that the incoming sample is outlier or not. Okay. Okay. Coming to this one class support vector machine, the second variant of this one class support vector classifier. No doubt this objective, because if you see this objective function, it seems like it is some sort of the objective function of support vector machine. And this model was developed by this Cook. The objective was to draw one hyperplane such that the target class, the plus one class is target class, and the rest of the sample either not present or poorly sampled will be residing on the subspace of the origin. Okay. So again, if you see this objective function, so the points which are closer to the origin, they are directly treated as the outliers. If you want to formulate this one class classification, one class support vector classifiers, so surely we must go for some latent space and we must compute the distance of point from the origin. Okay. If a point falls to the subspace of the origin, then we can say that the incoming sample is an anomaly or an outlier. Okay. So based on two basic variants, lot of several extensions has been made. Like in this particular chart, we can see that, okay, like you can see this one, we can extend that SVDD model towards some ellipsoidal data description so that you may get more flexible boundary. Okay. Likewise, we may have some more, optimized loss functions. Okay, so that the variant may be treated as the pinball one class support vector machine or the hinge loss one class support vector machine or rescaled hinge loss one class support vector machine, or we can deploy some fuzzy membership to data points such that our boundary may get more flexible to cope up the false predictions. So yeah, coming to these deep learning models, because these deep learning models are more trendy to nowadays. But what will happen, suppose we are equipped with single class samples? Then again, deep learning models are data crunchy, and basically they are always needed at least two well-defined classes. Okay. So in that case, what we can conclude that yes, deep learning models, we can extend deep learning models towards the anomaly detection, but again, we must have at least two well-defined classes. In such cases, we must basically balance the imbalanced classes, or either if the second class is not at all present, then we must assume some hypothesis about the distribution of the second class sample. But if you talk about the one class support vector classifiers, so they're able to work in presence of only the target class samples, with some prior assumption of the data distribution. Because it is not always important that we always look for the accuracy, because no doubt the deep learning models learn the features very well compared to conventional models. Okay. But still, if you talk about the performance and the computation power requirement, so surely this one class of representation classifiers are basically much better than these deep learning models because they need too much less computation. And no doubt they are able to work in presence of limited number of samples. Whereas if you talk about deep learning model, so you must have a huge, massive number of class samples, and we must go for the class balancing if the two classes are not balanced. Okay. Surely this one class operator classifiers are computationally expensive compared to deep learning models. And surely once we learn the things in better way, especially the target class, then we can avoid the wrong predictions. So this is all about the part 2. Then thank you very much.